So this lesson is on what is called conditional probability. So this follows nicely from the last lesson that we did on independent events, and when we learned to recognize how when two events were independent or dependent. We still want to be able to do that. We need to be able to recognize when two or more events are independent or dependent, but now we're going to look at how we determine the probability of these two events when the two events are in fact dependent on each other. So just to refresh our memory here, two events are dependent if the probability of one affects the probability of the other, or the outcome of one will affect the outcome of the other, or the outcome of one affects the probability of the other. If we have two dependent events, A and B, so if we assume that they are dependent, the probability of B depends on or is conditional on whether A has occurred or not. That's just restating our definition of dependent events. And in what follows here, we can often think of A as being sort of the first event that occurs. Okay? So A happens and then B occurs. So B is always depending on A and not the other way around. Okay? So what we are interested in is the probability of B given A, or the probability of B if we know that event A has already occurred. So we know what has happened in event A and how it is going to influence the probability of B. So when we say the probability of B given A, we use the symbol probability of B given A. And that vertical line there is read as the word given. Probability of B given A. And I think the easiest way to think about the formula for conditional probability, or the probability of B given A, is to imagine A and B in a Venn diagram. So I'm going to add my rectangle here around the outside, which represents my universal set. I'm going to have one of these circles represent A, and the other one represent B. If A is our first event, and A has already occurred, in our Venn diagram, we are somewhere inside this circle representing A. Okay? Like once A occurs, we know that we are somewhere in there. It could be because A has occurred. Now, once we're in there, okay, we're inside that circle, what is the probability of B already occurring? Well, the only way that B can occur inside this circle representing A is in this little area here where A and B overlap. So what is the probability of B given A? Well, looking at that diagram, okay, like our fundamental definition of probability is the number of ways something can occur divided by the total number of things that can occur. Our total number of things that can occur in this case is limited by the fact that A has to occur, which is the probability of A. Once A has had to occur, the only way that B can occur is in this little blue region here in the middle. We know from our discussion of Venn diagrams how to express that little blue region. That is the intersection of A and B. So that would be the probability of A intersection B. So if we want to figure out the probability of two events, A and B, okay, which are dependent, we can just rearrange this formula that we had up here. Cross multiply by the probability of A, and we get the probability of A times the probability of B given A. And this is the formula for conditional probability that we're going to be using throughout this section. Okay? Also notice that this is particularly important when we're looking at events involving the intersection, or we were looking at A and B. So with mutually exclusive events, we are interested in when we're looking at OR events. With independent and dependent events, we're interested in looking at when both of these events occur. So just to illustrate where this comes from a little bit, let's take a look at an example, a fairly straightforward example here. We've got a deck of cards. It's an extremely simple deck of cards, okay? It only has 4 cards in it. They're placed face down on a table. We've got 1 club, we've got 2 hearts, and we've got a spade. Let's change this a little bit. Instead of 2 hearts, let's say we've got 1 heart, a spade, and a diamond. Okay? So basically we've got 1 of each suit here. Okay? 1 heart, 1 club, 1 spade, and 1 diamond. We are going to pick 2 cards, okay, and turn them over. Pick 1 card, then pick another card. Okay? Find the probability that both of them are red. Now, before we get into the formula for conditional probability, let's just consider the entire sample space of what can happen, all of our possible outcomes. So I'll just sort of illustrate this kind of using a little bit of a table here. When our first card is turned up, we have 4 possibilities for this card. It can be a heart, a diamond, a spade, or a club. When we turn up the second card, okay, if our first card was a heart, our second card, well, we have 3 possibilities. It could be a diamond, spade, or club. If our first card was a diamond, our second card could be a heart, a spade, or a club. If our first card was a spade, our second one could be a heart, diamond, or club. And if our first card was a club, our second card could be a heart, a diamond, or a spade. So how many outcomes do we have in our sample space here? Well, a combination of our first card and one of our cards from down below constitutes an outcome. So we're going to have 12 possible outcomes. Heart and 1, 2, 3, diamond and 1, 2, 3, spade 1 and 1, 2, 3, club and 1, 2, 3. Okay? So 12 possible outcomes here. And we could answer this question if we want the probability that both of them are red. Let's just say both red. We could figure out the number of ways that we get 2 red cards looking at all of these. Well, let's see. We can get heart and diamond. We can get diamond and heart. And that's it. Okay? So 2 ways that both of these cards can be both red. So our probability of getting 2 red cards is going to be 2 over 12 or 1 over 6. Okay? So we can do this problem just by writing out all of the possible outcomes in our sample space. Let's try it again where we use what we've just learned about conditional probability. Okay? Let's give names to our 2 events here. We'll let event A be the event where the first card is red. Okay? And we'll let B be the event where the second card is red. We are interested in the probability that both cards are going to be red, so we want the probability of A and B. Now, if we didn't know anything at all about conditional probability, and we were approaching this question, we would start to work out the probability of event A, and then we'd start to work out the probability of event B. So let's just do that over here at the side. The probability of A is the probability of getting our first card to be red. Well, when we pick our first card, we've got 4 cards in our deck. 2 of them are red. So that probability is going to be 2 out of 4. Then we could go ahead and try to work out the probability of B. But when we go to work out the probability of B, we find that it's going to be dependent on what has happened with event A. Okay? If in event A, okay, the first card we picked is red, how many cards are left in the deck? Well, there are 3 cards left in the deck because we've already taken one out in event A. And if it was an A, if A occurred, if the first card was red, there's now only 1 red card left in the deck. So the probability of getting a red card for our second one is going to be 1/3. But if A does not occur, if our first one is not red, okay, then what's left in the deck? Well, if we've taken out a black one on our first choice, we have 2 red cards left in the deck out of 3 cards. Okay? So the probability of event B depends on whether or not A occurred, whether or not we got a red card in our first one. How do we know which of these 2 probabilities to use? Well, remember what we're asked for here. We're asked for the probability of A and B. So the only way both A and B can occur is if both cards are red. So we only want this probability that comes up if we assume that A has actually occurred and our first card was actually red. So this is the probability of B given A. It's the probability of B occurring assuming that A has already happened. Okay? And that's why we want this using AND events. An AND event, we need both of these things to happen. So A has to have occurred in order for us to get the probability that we want. So we want the probability if we assume that A has already happened. Which leads us to this formula that we had. That the probability of A and B is just going to be the probability of A, okay, the probability of our first event, times the probability of B if we assume that A has already occurred, or the probability of B given A. So this is just 2 over 4 times 1/3, which gives us 2 over 12, or 1 over 6. Okay? Which is the exact same answer that we had from writing out the entire sample space and counting the events.